That's the one which asks us to find the sum of the sines of a particular angle when you go all possible multiples of this angle. So you go sine of theta, sine of 2 theta, sine of n theta. When you look at the sine now, when you look at the trigonometric functions, and even if you're not looking at them within the context of complex numbers, you should think about the complex numbers and the bridge, the connection, this link between the complex numbers and trigonometric functions. Of course, this is a Euler formula. So here's the Euler formula, e to the I theta cos theta plus I sine theta. So if I remember my Euler formula, I may immediately take this unknown a, this big right-hand side. I gave you actually two versions of this a, the sigma notation and the expanded one, but I'll do the expanded one today. So you may immediately take this right-hand side and just alter it like so. Look at this. Here it is. You can say that a, because you see, sine is basically the imaginary part of this exponential. You can replace each of these signs with the imaginary parts of some exponentials. And that's the key step here. In fact, there are actually a few problems of this type in the yellow book. In each of those, this line of thinking will be helpful. Again, what we will do at the first step, we will replace every sign here with the corresponding imaginary part of some exponential. That's my replacement. Look at this imaginary part. I'll just put one single. Now goes my exponentials. This is the one which corresponds to this sign. Imaginary part of this exponential will deliver one sign. Imaginary part of this exponential will deliver this sign. You go on in the same fashion. This sign will be imaginary part of this exponential. Yes, it looks like geometric progression. Actually, I think I have it here somewhere. It looked like this. This formula. Sum of powers of q, from q to the power 1 to q to the power n. And we know the result of this, right? I remember it normally this way. You take the first element of your progression, you subtract the element of your progression which follows the last one, so you subtract qn plus 1, and you divide by 1, take q. For this particular expression, your q, here it is. The choice of q is this one. All right, so let's just directly apply this formula. If I apply this formula, I think I have a result here somewhere. Here it is. Right, so we just apply this geometric progression formula. The next step, of course, will be simplify this a little bit. It's on my phone. Simplify this a little bit. What would be your suggestions when you look at this? How would you approach simplification of this expression? Because you see, we expecting something pure real, right? Because if you look at the question itself, nothing here involves complex numbers, just sine function, which is a pure real function. So eventually, in your eventuality, your a must be a real expression which involves only real numbers. So, in fact, you have to just compute the real imaginary part of this expression. And what do you think would be a good approach to this? Okay, that's good. That one of you knows this trick. It's a very for people who do complex analysis often. This is a standard trick. How to deal with the expressions like this. There are a few questions in the yellow book which we can benefit from with some in those questions with this if you do this trick there. You try to make this expression sort of symmetric, or in fact, all of this based actually. This is a Euler formula. Here it is. All of this is based on the reverse version of this Euler's formulae. I mean, if you look at this identity, which we call Euler formula, and if you express cos and sine, or simply speaking, if you solve this identity for cos and for sine, you can do that. And if you solve that, you will have something like this. Your cos will be looking like this. It will be exponential ei theta plus e negative I theta over 2. And for sine, the solution will be ei theta take e negative I theta on 2i. In fact, we call both of these identities Euler formulae. That's why it's plural here. And I think I have here the beautiful bracket and the beautiful equivalent sign. All right. So, in fact, both of these identities are quite useful. And what we're going to do here, we will try to make this fraction, or in fact denominator and numerator of this fraction look like this bit, or look like this bit. And the trick to make this happening is what was suggested by factorizing properly. Look how we're going to factorize. So this expression under the imaginary part, look what I will do. First I factor out ei theta from the numerator. So from here, 1 ei theta gone. From here, 1 ei theta gone. What's left in this position? Perfect, 1. What's left in this position? E, I, and theta. 1 is gone. Now from this one, I do like a few multiplication in one go. You can reconstruct the details on your own later. From these remaining 2 bits, which I just said to you, I'm not going to show it to you in writing. I will factor out what was suggested. I will factor out, listen carefully, I and theta on 2, or half. I and theta half. Look what will happen there. So here's my factor, which I'm going to take out from the numerator, from the remains of the numerator after this one is gone. For this. So in this position it was 1. In this position it was 1. So what do you think will be there after this one also gone? In fact, it will be negative of this exponential, right? Because together they make 1. So in this position you will have this term remaining. Now, what will happen in the position of this exponential? E, or to the I and theta on 2. You see, by simple, well, not simple, it's a simple factoring, of course, but the choice of the exponential which we take out, it was an educated choice. We look at this bracket. It looks like this, doesn't it? Like a numerator of this side. With the proper choice of theta, of course. If you take n theta in the position here, it will be this enumerator. So in the next step, I will be able to condense this bracket down to just sine of a proper angle. And let's just see what happens at the bottom. At the bottom, again, I factor out a proper exponential to make this happening. What do you think the proper exponential will be in the denominator? If you go half, if you factor out half, look what happens in the brackets. In the position of this unity, you will have negative of this theta half, because if you just restore it back, if you multiply these 2 together, it will be this 1. In the position of the next exponential, it's your half. Oh, these exponentials can be combined together. Somehow we will combine them later. But these 2 brackets, this one, this bracket, and this bracket, now can be replaced with the sign of some proper chosen angle. That's the replacement. Look at this. A is the imaginary part. If I combine all of these exponentials, this exponential, this exponential, and this exponential, will be this one. Now, for the brackets, I now have 2i sine theta n on 2 and 2i sine theta on 2. Well, we're almost done now. We can cancel out this 2i. We can cancel out this 2i. And because this is the imaginary part, now in this expression, in these brackets, in this big expression in the brackets, the only component which actually involves any complex numbers is this exponential. This I is sitting here because I didn't cancel it yet, but it will go momentarily. But this one, that's the one which carries actual complex numbers. And when you go after the imaginary part, of course, you will be after the imaginary part of this exponential. And the imaginary part of this exponential, again, comes from the Euler formula. So if I use that, let me just zoom out a little bit. Yes, actually, you're right. I didn't mention that step. Thank you very much for this observation. In fact, if you do it properly, I just skip this quickly, because we got negative here, and positive here, and here like in the opposite order, positive here, negative here. You have to take for your angle negative of these ones, negative theta n on 2 and negative theta on 2. But we know that sine is the odd function, so this negative can be taken up here next to this 2i, and this negative, the negative which was just mentioned, can be taken up here, and we can cancel those 2 negatives. Okay, it's something which I overlooked when I was preparing this, but it doesn't really affect what's happening on the screen. If you just take this exponential, the expansion for this exponential via Euler formula, here it is. So this exponential, just this expansion. And because we only care for the imaginary part of that expansion, we just take this sine this sign, and we multiply this sign by this fraction, and that will be the result we're looking for. Here it is. Sine, imaginary part of this exponential, times the fraction, where 2i is gone, and when this accidental negative also is gone. And that's the answer they expect from you. Sorry, this slide. Just look at the just now. Let's just look at this whole solution together. Look how beautiful it how beautifully we use a few very general ideas you know from your school, like geometric formula and some complex numbers like Euler formula. And we were able to condense this long expression, which involves lots of terms, into a very nice simple one, which involves only 3 factors. You like it? If you like this thing, you can extra practice this. You can do a few modifications to this question. I'm not sure if a yellow book has these modifications, but you can, and you can try to see what changes and what kind of result you will see for those modifications. And I listed those modifications here for you, but I need to bring it, roll it up a little bit. Let me just roll it up, and I'll show you these modifications. For instance, you can ask the question, what will happen if you sum up coses instead of sines? This is very easy modification, right? In the whole solution, it will be very minor alterations. You may replace this imaginary with the real, imaginary with the real, imaginary with the real. And so in this expansion, you will take this cos instead of this sine. So all you had to do, in order to fill in the position of this question mark, is just replace this sine with cos. And that's already the answer to that. Trickier question, or trickier level of modifications will be needing if you go after sum of sines or coses with alternating signs. So when you go sine theta negative 2 cos, and then plus, then minus, then plus, then minus, and so you alternate the sign according to this law, negative 1 to the power n take 1. So when you go with the alternating signs, this method still can be adjusted to alter this, to match this new question. Yeah. In other alterations, you can do the question and try to do the same method. Is when you go, again, when I say sine, you can also do the cos alteration, but I'm not putting this on the slide. When you go sine theta plus 2 sine 2 theta plus 3 sine 3 theta. So you introduce an extra factor, like this one. This one also can be approached with the same method, although for this last one, you would need to find a suitable replacement for the geometric progression formula.